presenting on behalf of Group 4, and the topic is adversarial neural cryptography. Looked at this in the last presentation, and some of the progress points will be elaborated here. A general overview of the things that we've been doing. We had talked about synchronization of neural networks to learn the same function in the forward and reverse direction, or in the to have two networks learn.
Synchronization of networks. Neural networks were trained to communicate such that one network learns the inverse of the function learned by another. That's fine. एक रिसीविंग एंड पे होगा और एक सेंडिंग एंड पे होगा.
Yes.
तो जो रिसीविंग एंड वाला होगा वो कैलिब्रेटिव होगा, इनवर्स मॉडल होगा.
Exactly.
ठीक है, चलो आगे चलो.
So this is one thing, and the another thing is then after we have reliably trained two networks that we know that these can communicate in such a way, we introduce a third party into the system, which is the adversary, and we see how they perform against that adversary in a cryptographic sense. Okay, so a general overview. Two approaches we have been working at. One is the ANC model, the original ANC model proposed by Martin Apadi in the 2016 seminal paper on this topic, and the other model is that we have worked on is it's called CryptoNet, called that by the authors, by Martin Coutinho. This was the 2018 paper. So these are two approaches we've worked at, and they're very similar but with slight differences. Now, the tools and libraries, Python 3.6 has been the main runtime environment. PyTorch 1.6 is our live machine learning library that we're using.
Ali Samar, you explain your work, है ना? In today's presentation, you explain your work, whatever you have done.
This the work will come.
Okay.
So yeah, TensorBoard and Matplotlib are the plotting libraries. So the ANC model. We know the overview, general overview, that there are two networks.
Can you show me your objectives once more?
Objectives were in the last presentation. I'll have to bring that up.
No, your objective should be integral part of your all the presentations.
Okay, I've not
Your
added them to
objective.
this because I thought I'll only talk about the progress.
No. It is not like that. Whatever you presented, then in final presentation you won't present. Always your presentation should be complete presentation.
Okay. So the main objectives were that first of all we have to see is it possible to train two networks such that they communicate reliably, such that they learn that inverse function thing. First objective was that. Then the second objective was to train networks such that we can reliably encrypt a plain text such that third party is not able to understand it, such that a third party is not able to decrypt it or predict the original text. That is the second main objective. So
that is always an objective.
Yeah, of course.
Your network should not be get hacked.
Yes.
Okay.
So we had seen the ANC model before. There are two neural networks, Alice and Bob, and the plain text goes to Alice. Alice produces the ciphertext. Ciphertext goes to Bob. Bob produces their version of the plain text, PB. Then after we have trained this chain to be able to do this task, then we introduce the third party Eve into this system, to whom the ciphertext is sent, and Eve tries to produce their own version of the plain text, PE. And we observe the loss of these networks. Now let's talk about the structure of this network, internal structure of these two neural networks. First of all, Alice and Bob have the same structure. They have the same layer structure, and we have two inputs which are given to them. One is the plain text E, and the other is the key K. So basically what these are just lists of binary numbers, zeros and ones. Both of these are lists of numbers. So we concatenate these inputs and we send them to Alice and Bob. Now the first layer is a dense layer with the ReLU activation, rectified linear unit. So the first layer is dense layer, which takes the inputs. Then we have four convolutional layers, and these are the
What is ReLU? ReLU is contemporary to what activation function in a shallow neural network?
to ReLU by itself is also used in shallow neural networks. ReLU is a
It is came into the picture only with reference to
deep networks.
deep neural network,
Yes, it did
because
come into the picture.
of
Yes,
to make it more algorithm more efficient,
yes, exactly.
um,
Because the thing,
fast, and also because it will deep neural network will have more number of neurons and all.
so the precursor to this was that we everybody was using sigmoid activation, and
Yeah.
so sigmoid activation. The problem with it is that
Simple
it's
activation is basically highly non-linear kind of
yes,
uh,
yes.
function. So it has been piecewise linearization done for that it is ReLU.
So
चलो ठीक.
yeah, so now we have four convolutional layers. These are one-dimensional convolutions, and the number of bars that you see, this corresponds to the number of output channels. So the first layer takes one channel input and outputs two channels. The second layer takes an input of two channels and outputs again two channels. The third layer takes input of two channels and outputs four channels. And the last layer is supposed to club all these together, takes an input of four channels and outputs one channel. Now all this convolution adds dimensions to our input. This is just how the library works. And so for that we have this flattened layer which removes those dimensions, which are basically just if you put the same list inside another list. So this layer removes all those dimensions and produces our ciphertext, final ciphertext. So this
So
is
it is encrypted data you are getting here.
exactly. So this is the net structure of the Alice and Bob networks, and this is the high-level structure of the entire network. You can see that we send P and K to Alice. It does its job here, and the ciphertext is produced here. Now this ciphertext goes to Bob and also goes to Eve. Uh, this dotted thing means there's a copy, and Bob is also given the key. Now, the same thing that Alice did with plaintext, Bob does with the ciphertext. It concatenates the ciphertext with the key and runs it through its own network and produces PB here, right? And Eve takes a copy of the ciphertext, runs it through its own network. Now, this network of Eve is the paper suggests that any sufficiently complex network can do this. So we have taken two dense layers and four convolutional layers with a different shape, but essentially the idea is the same. It takes in the input and produces a ciphertext or a plain text output, PE here, right? And this is a high level structure. So the loss function that we are using, let's talk about uh, how the loss is measured. So the communication between Alice and Bob has some loss, meaning that B and PB, sorry, the Bob's version of the plaintext will have some differences. So to measure how much it is different, we use the L2 loss metric, the mean squared error, and we put PB and P through the L2 loss, and we get the loss for this Alice and Bob network. The error of decryption of Eve is measured also by the L2 loss metric, because again we have uh, what we were expecting and a certain version that has been given to us. So we put E and P through the same loss metric and we get the loss for Eve, right? This is the adversary's loss. So these are the two loss functions that we've used. And the training, how do we train? So, first of all, the paper suggests that you use batches of 4096 samples. Now, this proved to be a bit difficult for us to train on because we need a lot of epochs and a lot of changes, and we don't have the hardware capable of that. So we have instead opted for mini batches of 64 samples and a larger batch of 256 of these 64 samples over 16 epochs, meaning 16 times we repeat this process. So we get a total of 262,000 samples, and this seems to be almost the same number of samples as the paper. They've used 250,000. So this is how we separate our batches. The paper suggests L1 loss and also the measuring it against each other using a quadratic equation. We have tried to use L2 loss and also binary cross entropy loss. Binary cross entropy did not give good results. L2 loss seems to give the better results than L1 because it doesn't take into account, it does take into account, but it sort of ignores the positive and negative versions of the differences. So if your answer is greater by a certain degree or less by a certain degree, that is the same to the L2 loss function, and that seems to be working better for us. And we've used the Adam optimizer. The optimizer is something that's necessary, and we've used the optimizer with a learning rate of 0.0008, which is 8e minus 4, and 0.00001 weight decay, and this is the Adam optimizer's parameters. So again, the methodology.
So as far as the learning rate is concerned, so you are supposed to give the learning rate, or this Adam optimizer algorithm, it optimizes the learning rate.
We do give the learning rate, but Adam is capable of changing this rate as it goes along.
To
So
optimum value.
yeah, sorry.
To optimum value.
Yes, to an optimum value. So
And this is your delta weight weight decay.
yes, this is the delta. Yes, exactly.
So it will always be minus.
No, it's not a minus rate. This is e minus
You are
5
talking about
means
the,
10 to the power minus 5.
then you are saying weight decay.
Yes.
Always decay.
Yes, always decay, because we assume that we take a too big step.
And
like-
whatever initial weight you have chosen or taken, that will be modified in the lower direction only.
Yes, because we assume that we take a bigger learning rate. We don't start with a very small learning rate. We always overestimate the
That's-
learning rate.
I'm just talking about the weight decay.
So that. So again, the methodology of training is that we first train without the adversary. We train the two networks to just communicate with each other and see how their loss decreases. And then they are the same. The networks which are trained to do that are retrained with the adversary involved, right? So this is how we.
Just 1 minute, Samar. In the real situation, how come your if will have the training data,
Oh,
the third party?
yes. So that is a thing that we have to, because of course, two parties communicating of the internet, for example, will not have so much time to train, right? That is true. But
That-
we hope that if you have one trained model, then you can, there is a way of adding additional pipelines to it so that it becomes a few shot learner. And a few shot learner is able to synchronize itself.
And then that is fine. That is fine, Ali Samar. And then your neural networks are having attribute of generalization also. That is utilized here. Okay, but I'm talking about the third party. Third, because you are sharing the information with the as far as the another end, whoever means is sitting, you are sharing that. So both the networks, desirable networks, are basically trained with the known data.
Yes,
But a third party is not having that known data.
exactly.
So how in a practical situation, how this third party will train its own network?
The third party should not. That is the whole point. That if you don't have that one piece of information, then you should not be able to produce the correct plain text.
That is fine, but in this case you are studying the vulnerability with the third party also. Like if jo hai,
Ah,
if anyway it is a threat,
yes,
so if will also have a network, is having a network.
yes,
So how come this network will be trained
they don't
and
have
it
access
is
to
not
the original, yes, plain text.
key also? So somehow means how will you simulate this
Our-
network?
In our
Practical.
Yes. Yes.
What I'm saying that in practical situation, obviously they are not having key, so they won't be able to do the means description
Key decryption. Yes.
decryption. But they are means they are means our data is vulnerable to such kind of problem.
Yes.
So how this third party will train its network so that it is a threat? If it is not able to train at all, then there is no threat.
Yes. So see, the thing is that in the real world, the threat is not coming from a neural network. Because the threats are coming from real human attackers and real human people who are trying to see the point of having Eve here is not to say that this is the threat. The point of having Eve is that uh, to produce a encryption scheme that is better than random chance. So what happens is we have our plain text and key, we produce a ciphertext. Now this ciphertext might not be very different from the original, right? You, it might be so that you can look at this ciphertext and or say that array original might have been this, right? By just pure guessing. So the point of having Eve here is to avoid that. Point of having Eve is that if this neural network is able to tell what the original was, then the human will certainly be able to tell, right? And if Eve becomes stronger and stronger.
You want to prove if we are having this kind of system, so it is very difficult for the third party
Yes.
to break it.
Yes.
Okay. Okay.
So yeah, so the methodology I talked about and the networks that it trains that with. Right. And let's look at some of the code that we've written for this. And here it is. This is the code for the ANC model. Now we use PyTorch, and we have defined a class for a key holder network. This is the class for the key holder network. There are 5 basic layers. The entry layer, this entry layer is just an identity. Identity layers means it doesn't transform the
You
input.
simulated the convolution neural network, eh?
Sorry.
1, 2, 3, 4.
Yes,
You
yes, yes.
simulated the convolution neural network
Correct.
1, 2, 3, 4.
Yes. So this
Okay.
entry layer is just to provide uh, shape input problems. It is to avoid there are problems with input shape. So to avoid that, we have this input layer. Anyway, so then we have this fully connected layer, what we call a dense layer, and it takes 2 times the block size as the input, meaning that this block size is the length of P and K. Okay, so it takes twice of that because it's taking P and K, and it gives an output of the same size, right? This transforms, this is the first transform. And then there are the 4 convolutional layers. The parameters of these layers are as they have been suggested in the paper. Output channels as they've been suggested in the paper, 2241, and kernel sizes of 2211, and then the strides also. This is the forward pass function. This is how the data flows through the network. So we first put the inputs through the entry layer, then we put them through the FC1, then okay, this is supposed to be the
Conversion 1.
so this is the
Okay.
first conversion. Then we add the dimensions to the input to be able to go through the convolutional layers, because the convolutional layers require that you have extra dimensions. So then we add 2 dimensions, and then the 4 convolutional layers happen. And after that, we have the hard sigmoid function at the end. This hard sigmoid is nothing but the sigmoid function with different parameters. It just it what it does, doesn't give us a smooth output. It gives us a either on or off output, so that we are able
0.
to
0.
0 or 1 output, so that we are able to convert that to binary, right? So this is the key holder network. Then there's the attacker network, almost the same, but the difference is that the attacker doesn't have the key. So we have to have a network which doesn't take twice the block size. You have to take a network that takes 1 times the block size. So it has the same entry layer FC1, which is the dense layer. Then there are 4 convolutional layers with the same parameters. Again, the same thing happens here, right?
So you are training this attacker also with the same data.
Yeah, exactly. Yes. Now, Data and pre-processing. First of all, we
This is your,
have
this is your encryption stage, no?
yes. Now, first of all,
Okay.
we have a block size variable. This block size is how long your inputs are basically. So 16 indicates that they are 16 bits long, and we have a key, right, and a plain text, a list of plain texts. Now, if I can just show you how this is, you know, visualized in the program. So a key is a list of zeros and ones, something like this, right? And the plain text is
So
a
this will be concatenated with each data, no?
yes, exactly. And this plain variable here, it's a list of lists, something like this. Uh,
That's fine.
okay, so each of each of these plain texts will be concatenated with this key and sent through the networks, right? So this is how it works, and we have 12 batches, and there are functions to recalculate these so that we have fresh data. Yeah, so
12 batches means
12 batches
12
is
data points.
no, 12 batches means that this plain text ka length is the number of plain text that we have is 2048 here. So 12
Mhm.
times into 2048. So that is what is meant by batches. So that gives us what,
Okay.
24,000 samples. So now we initialize the networks. We initialize Alice and Bob as key holder networks, and we initialize Eve as the attacker network, right? And we use the loss function L1. Here you can see that we have tried MSE and binary code
Initializing your
sequence.
network.
Yeah, we initializing our network here. Basically, we've used MSE in this, so I'm going to just
Initial
uncomment.
parameters you are supplying,
Yeah,
learning rate and all,
yes.
to
These are
all
the
three
optimizers.
networks.
All three networks, yes. These are three optimizers. And yeah, now we come to the training loop.
You are
Uh,
running.
yeah, so these three lists and these are just to store the losses so that we can plot them later. And
Where is the stopping?
there are two stopping criteria mentioned in the paper. First, you will see that in the loop right now. There are two criteria. First of all, that if the network doesn't train by 150,000 samples, then we say that they are not going to converge. So we
Okay.
stop training there. The second condition is that if the learning is slower than 0.0005, then we stop the training because we think that the training has the rate of decrease of loss has stopped. So yeah, so we can see that in the loop. We'll see that right now. So this is the training loop. We start training. We convert P to a tensor. Every plain text in P plain, we convert that to a tensor. We convert the key to a tensor, and we send those through Alice. Now this torch.cat function, this concatenates them along the zeroth dimension. So these two are concatenated and sent through Alice, and we produce a cipher. Now the cipher is detached from the graph. There is a computational graph in PyTorch, and it is important to detach it because otherwise the backpropagation step calculates the gradients all throughout the Alice network also. So we don't want that. We want separate gradients. So that's why you have to detach it from the computational graph. So anyway, now we do the same thing with the Bob. We concatenate the cipher with the plain text with the key K, and we send it through Bob, which produces PB. And we take the cipher, just the cipher this time, and we send it through Eve, and that gets us PE. Now this little loop measures how many bits are wrong in Eve and Bob, and we append those to the lists respectively. How many bits they got wrong, essentially. So this is that. Then we start measuring the losses. So the loss function takes in the input of PB and P. This is the Bob's reconstruction loss, how wrong Bob is about the original, right? So this will give us a mean squared error of these two tensors. And E's reconstruction loss similarly is PE and P's differences, how many bits they are wrong about. So this is Eve's reconstruction. Now Alice's loss. Alice has to take into account how how much Bob is wrong and how much Eve is wrong. So it has to take into account both these things. So uh, Alice adds Bob's loss and subtracts Eve's loss from it. This beta and gamma are two variables that I have defined to control how much Alice is affected by Bob and how much Alice is affected by Eve, right? And why subtraction? Because in our whole algorithm, the whole point, the whole way of learning is that we reduce the loss. So the losses that you want to reduce are positive, and the losses that you want to increase are negative, because negative will be higher. Uh, a higher negative value is a lower value. So yeah. So Eve's loss is negative in this case. So this is Alice's loss, and this is the quadratic loss that the paper suggested. This is the equation for that, but this didn't seem to work very well for us, so we've commented this out. We did try this out. We have a lot of graphs to show that for that. Anyway, so now we first backpropagate Bob's loss, then we backpropagate Eve's loss, and then we backpropagate Alice's loss that we calculated over here. What this backpropagation step does is that it changes this output loss and sees how much the weights are affected. So what you have to do is you have to calculate the inverse gradient of the weights with respect to the loss. So how much do you change the weights such that the loss decreases? This is what that backpropagation step does, and it calculates gradients for all the neurons in the entire network. And it's a very time consuming, it's not a very time consuming step, but again, it used to be a time consuming step with modern computers. Anyway, then we step the optimizers. This optimizers will take into account how much the changes were from the last iteration, and they will change the weights accordingly. So backpropagation only calculates how much the gradient is, the optimizer makes those changes. So that is the thing. Now here we see the stopping condition that we were talking about. We see how much Alice's loss has changed from the last iteration. This -1 indicates the previous previous loss. So there is delta of Alice, delta of Bob, and delta of Eve, meaning how much they've changed from the last one. And we calculate the average of these. If the average is less than this value, which is 0.00005, so if that is there, then we say that the training has stalled. The losses are not changing any further. So we break from this loop, and then if this doesn't happen, then we append the current losses to the list of losses, and then we continue training in this loop, right? And on every batch iteration, we recalculate the key and recalculate the plain text so that we have fresh data every time, right? So this is the basic idea of the training, how the training is working, and then we have some of the plotting that we are doing. These plots we will see in the
Now, where is the testing?
yes. I couldn't hear you, sir.
Where is the testing?
The testing is
Once, once your training is stopped or stalled, then how will you check the its generalization
yes.
property?
For
How?
that, we have, first of all, we have these plots. We have to look at the plots and see, is the loss decreasing properly? Is it
With
happening as
respect to training data?
yes. So I'll just show you these plots. Now we've looked at the code, and we'll look at some of the plots. So this is the first plot where we don't have the adversary involved right now, and you can see that initially the loss stays at a constant value and it jumps up high. Now when it jumps up high, this indicates that the networks have started to learn, meaning that the higher loss is now affecting the networks. So from this point, the loss starts decreasing. Now this is what we expect, that
Initially, your network will diverge.
sorry.
Initially, your network is diverging.
Yes, yes. Initially, the network will diverge because again, the loss has not starting. The back propagation hasn't started affecting all the weights in the network. So initially, of course, the loss will be high, and then as we train with more and more samples, this samples here actually means batches. So as we have more and more batches, loss starts to decrease. You can see that it goes down close to zero, but doesn't quite reach exactly zero.
But
But
Samar, generally, um, your your back propagation algorithm is basically gradient descent algorithm.
yes,
So initial divergence or increase in um, loss, uh, it mathematically is not explainable.
it's the thing is that initially,
As far as gradient descent algorithm is concerned, formula is very simple, that it changes the weight in the direction in which your loss decreases.
that is true, correct, that is true. But the thing is that the weights that we have initialized, when you initialize the weights, they are always random. The problem with that,
And
this is the thing with that.
initially,
Sorry.
initially it should have maximum error,
Yes,
but in first iteration, because your algorithm will come into the picture,
yes,
and it will always set the weight in the direction in which your loss will decrease.
yes.
That is what the formula through which your on which your algorithm is working. Your equations are derived from that formula.
Hmm.
Delta W minus delta W upon delta T is equal to delta minus delta E upon delta W. That is the gradient descent formula.
Yes.
And using this formula, all weight modification equations are derived.
Yes, see, the thing is that the optimizer might not always work exactly the same. The algorithm that you're talking about, gradient descent algorithm, that is the stochastic gradient descent (SGD) algorithm. And the thing is that the SGD algorithm, yes, it does decrease smoothly from the beginning. It doesn't diverge initially. But the thing with the Adam optimizer is that it might at times do this because the weight initialization is random. So yeah, so we start actually.
Weight in a initialization is always random.
Yes,
This algorithm basically converges to the most and obviously other things are set by the optimizer you are using as far as the learning rate is concerned, or and all these also means parameters are changed in the direction in which in the direction of convergence only.
yes, yes.
Anyway, we continue.
Okay, so we can see that the loss decreases as is expected with more and more training, and that the network learned to communicate. This is the initial synchronization step, right? And the bit error is measured, right? The second observation that we take is how it affects how it affects the network when the adversary is added. Now, initially we don't have the adversary, and when we add the adversary, the networks are supposed to behave differently. Now, in this graph, we can see that the loss starts out high and starts decreasing. Now, the loss of Bob, which is blue, and sorry, Bob, which is orange, and Alice, which is blue, this starts decreasing and stalls at a point. Now, at this point, we can say that the networks are not learning any further. So we can say that the losses of the networks are being you know affected by a small degree by Eve, because if Eve is introduced into the system, we expect that the rate of change will be different, right? And if you see in this case, the rate of change has not changed a lot. By 500, by 500 batch, by the 500th batch, we have reduced by around 1.25 loss units, and in this it's almost the same thing here. So the gradient of the rate of decrease of the loss has not changed. This means that although Eve is trying to change its loss, which you can see by the oscillations, um, the network is not being affected by Eve in this simulation. Now this is a problem that was inherent to this network because
I'm not able to understand one thing.
yes,
Your Alice, Bob, and Eve networks are independent to each other.
Yes.
Means as far as Eli's network is concerned, it is trained separately. Bob network is concerned, it is trained separately, and if's network is entirely independent.
Yes.
So how come these three networks, means when if comes into the picture, how will it affect the training of two other networks?
Ah, okay. I'll just show you the loss equation. The thing is, Alice's loss depends on Eve's loss, right? If Eve's loss is high, Alice's loss will be low. And if Eve's loss is low, Alice's loss will be high. That is the relation between these two networks. They are connected by the loss. This is the whole concept of the generative adversarial networks, that we have uh, one loss affecting another network, right? So Eve's loss is affecting another network, Alice, and Alice's loss is affected by Eve. So when we backpropagate, essentially what we're doing is we're taking into account Bob's loss as well as Eve's loss in Alice's training. So that is why we expect that Alice's training will be affected by Eve.
Okay, okay, okay.
Right. So yeah, so we expected that the rate of decrease will be lower, because again, if the adversary is involved, the training should be slower, right? They should be sort of fighting against the adversary. But this is a problem that is inherent to this network, because if you see Eve's job, Eve's job is too difficult in this case, because it has to look at a ciphertext and predict the original plain text, which is for a neural network, it's a very difficult job. So Eve doesn't is it's not able to train very well. So that is why it doesn't affect the two networks very well. So to have an improvement over this, we have some of the improvements that we'll talk about later. So some of the results that we had from this, that the models do learn to effectively communicate, that we saw from the first graph, but the encryption scheme is weak, because Eve in this case is very weak. So the encryption learned is weak, simple enough. And the problems that we have with this is that Eve's job is too hard, yes, so that its loss never actually decreases. And the bit error remains relatively high, meaning that even though the loss is decreasing, the number of bits that is incorrectly predicted is high. And this we have to take into account. Another thing that we have to look at is that because we are giving zeros and ones as the output, we are giving whole numbers, or whole numbers as the inputs. The gradients tend to explode. The thing is that neural networks tend to work best with numbers between 0 and 1, which remain in that decimal range. So the gradients tend to become very large very quickly if you have whole numbers involved. So that is a problem that we had while training uh, the networks
Now,
minus.
if your gradient is sharp, then there is a problem,
Yeah.
because you are using basically you are sharpening the gradient slope of the sigmoid function.
Yes. So
If you are going,
yes. So now, an improvement over this model that we have worked on is the CryptoNet model. The name is suggested by the authors themselves. The citation is given below, and this is an improvement over the model, and it tries to make the adversary stronger, because of the simple observation that the stronger the adversary, the stronger the encryption learnt. So this network is, as far as Alice and Bob are concerned, it's almost the same. The the changes that they introduce are that instead of a plain text that is randomly generated, what we have is that we generate two random plain texts, P0 and P1, right? And this is done by, essentially it's done, for us it's done randomly, but you can have a random generator function here which does this job. It's the same thing. Anyway, so we have two plaintext, 0 and 1. Now we choose a number, 0 or 1, randomly, right? We choose a number randomly and take that plaintext and send it to Alice. So we have two plaintexts, we choose either 0 or 1, we don't know which, and we send it to Alice. And what Eve does is that it takes both of these, 0 and 1, looks at the ciphertext also. So there are three inputs now, P0, P1, and C. These three inputs go to Eve, and what Eve tries to do is that it tries to predict which of these two plain texts the ciphertext came from. So it gives a probability between 0 or 1. If it says 0, then that means that plaintext 0 was encrypted. If it says 1, then that means plaintext 1 was encrypted. So it tries to tell us which of these two was encrypted to form this ciphertext. So in this case, Eve's job is much easier, so that because it has to predict one number instead of a whole array of numbers.
But listen to me.
Yes.
If is having access to P0 and P1, so
Yes.
what is the need of decrypting it?
See, then again, the need of the point is not to the point is not to say that Eve is a perfect attacker.
This is the information we want to transmit with the security.
Exactly. So if Eve's job is easier,
If
let's say,
is having access to this data,
but Eve doesn't know which of these two was encrypted. Eve only has both of them, and it has the ciphertext. It has to tell which one of these was encrypted. And this is a standard technique used in cryptography and security. It's called the chosen plaintext attack. What you do is, if you're trying to attack a server or something, let's say, what you do is you
as far as attacker's job is concerned, they try to get the ciphertext
yes,
and they try to decipher the ciphertext.
yes,
That is what is the attacker's job.
yes.
But they should not be aware of the main coded message which was
But that is not always
ciphered.
true. That is not always true. The thing is that you have
If they
access.
are having access to the actual information, then there is no need to, because
But the
whole picture is in.
the point is not to see what ciphertext. The point is not to decrypt just one ciphertext. The point is to see if Eve can learn the same encryption scheme. Because see, let's for example take the example of WhatsApp, right? Every time you send a message, the keys in your phone change, right? So an attacker, if even if they have access to your keys, even if they have access to your plaintext, they can only decipher one message, right? But if they have access to the entire scheme, then they can decrypt your entire set of messages. Every message that you send from now on will be able to be
That's correct.
decrypted. So that is
That's
the
correct.
point of Eve. So the stronger the adversary, the stronger the encryption scheme. So this is the network that they suggest using. And yes, so all right. So this is the structure of the network. At this point, we introduced two functional blocks in this network to combat this problem of converting ones and zeros to numbers. We introduced two functional blocks. First of all, we have this f block. This f function is the arc cos of 1 minus 2b. B is the bit. Every bit goes through this function, and 1 minus arc cos of 2 times that gives us a number between 0 and pi. So arc cos is just the cos inverse. So the input range is either 0 or 1. The output range is either 0 or 3.14, which is pi. So this function converts that 1 0 input into numerical input, into uh, basically fractions of the circle. So we can say that now we have a sort of numerical input between 0 and 1, and you can divide this by pi to get a number between 0 or 0.999. So yeah, this function they introduce, and the inverse of this function they introduce to reverse this process, and that inverse is 1 minus cos a by 2. So the input range can be between 0 to infinity here, and the output range is either 0 or 1. Simple enough. So yeah, these are two functional blocks that they've introduced into this network, and the way that they're arranged is that we take the inputs p and k here as before, and we put them through this functional block first, making them into numbers, into radians. So so that now we are operating on numerical values rather than binary values. So again, the network structure we can look at, there are two dense layers this time. This network we have arrived at by experimentation. Their network that they suggested was very simple, and it was not able to learn anything. So this we have arrived at by experimentation. And the first two layers are dense layers with ReLU activations, you can see here. Then there are four convolutional layers with a slightly different structure this time. The 2421, that's the number of channels, and they have all sigmoid activations. Again, then there's the flattened layer.
How, how, how did you converge to this number of channels?
Uh, Basically, this number of channels is approximately the same that was suggested in the previous paper, but
Okay.
so basically I tried some changes, and this four channel module before the second in the second layer of the convolutions tended to work better. So yeah, this can be changed. This is not a hard and fast model. Of course, we are still experimenting with these.
It is decided by the while training,
Yes. No, sorry.
whichever gives the.
No, we actually do multiple lots of iterations of training. We see which has the best decrease in loss, which has the best uh, characteristics. So that way we change, refine the model.
Okay.
So again, there is the flattened layer, and then there is the F inverse layer. Now this will do is that your network is giving you numerical inputs which are between 0 and 1, and this will convert it into binary numbers, and you then get your ciphertext C. Right. So this is the structure of the network, and this is the high level structure of the network. You can see everything going on. You can see that Alice and Bob are doing their job as usual, except with the functional blocks this time. And there's this plain text generator that I talked about. You can essentially, this is not a generator in our code, but you can delegate this job to a function, and that will become a generator. It's not. It's the same thing. So we have this plaintext generator produces two plaintext P1 and P0, and one of those goes to Alice, and both of them concatenated together become Q, right? And so basically this Q indicates that you're sending both of them to Eve, and Eve also takes C as the input and concatenates them, and this is the same thing as before, right? So this is the
Mon- no, stay.
okay. So this is the
Uh,
high level structure of the network. And now we can look at the loss functions. In this case, E's loss is measured by the binary cross entropy loss metric. Now, why did we choose this? Because Eve has to predict two classes. It has two classes which it can predict 0 or 1. And the BCE loss, the binary cross entropy loss, it tends to it does this exact same job. It measures your loss across two classes. So if you can just quickly look at the equation for this loss metric, you have your yi, which is the y, which is your prediction, and you have the log of the actual value, which is p of yi, meaning that what you initially gave it. So this is y times log of x plus 1 minus y times log of 1 minus x. So this will give you a loss metric that increases with your confidence in a prediction and decreases with your confidence in a prediction. So it takes into account um, how confidently you are saying that it is either this class or that class. The plot of this yeah so the plot of this of this equation can be seen here, and you can see that if the class is 0 and I give a 0 prediction right here at the bottom right, then the loss is low, right? But if I say with a high confidence that the class is 1, then the loss is very high. And vice versa, if the class is 1, if I say the class is 0, I get a higher loss. If I say that the class is 1, that I get a low loss. This is what the binary cross entropy loss does. And a general form, more generalized form of this is the cross entropy loss metric, and we might not go into that right now. So yeah, let's look at some of the code now. Yeah, so the training parameters are almost the same, and we have almost the same training structure. So yeah, right now, uh, Now we are again using a key holder network class, right? We have again the identity layer. This time we have two fully connected dense layers. One takes in two times the block size, which is p and k, and outputs four times the block size, right? And the second dense layer takes in this output from this layer, which is four times the block size, and gives us a feature size of two times the block size. So what this by this we hope what will happen is that because we are expanding the layers out, we expect that the p and k, the plain text and key, will be mixed together in these dense layers. So the outputs of these should be a sort of mix of the two. Again, then there are the four convolutional layers, and we have the forward pass, which gives us the output. So again, we are putting it through the entry layer. Now we are putting it through the functional block, which is a arc cos of 1 minus 2b, which is expressed programmatically this way. Then we have two fully connected layers with ReLU activations, and then again we add the dimensions. We go through the four convolutional layers, and instead of just giving us the output, we go through the f inverse, which is 1 minus cos times sorry about this, cos times 1 minus cos of input by 2. So this gives us a number, and then we again pass that through hard sigmoid, because hard sigmoid gives us even better results with binary numbers. So we do that. Then again, the attacker network is very different in this case. We, instead of convolutional layers, we only have dense layers, and it takes three times the block size, which means it takes three inputs, which is p0, p1, and ciphertext, and then it again goes through it goes through the layers this way. This also has the f and f inverse functions here. You can see those, and this is the initialization function. We'll talk about this later. Now, again, we have the same type of key. We have the same type of plain text. Instead of one plain text, we have two plain text this time. This is p0, this is p1, and with these, with these two, we have a list of plain texts. Then we have functions to recalculate them, and now we start initializing the networks, and we start initializing the weights. Uh, then we declare the mean squared error loss for the initial training, and then we also declare the binary cross entropy loss, right? A major difference that we have with the original model in this case is that we have clubbed together the parameters of Alice and Bob into this optimizer for Alice and Bob together, and this gives us much better results instead of having separate
So,
optimizers. So this is there. Then we have a separate optimizers for Eve. Now we go into the training loop. This is the important part. We take the 0th x, the 0th position in the plain texts, and we say that that is p0, and we take the 1th position, which is p1. Now we choose a random number, either 0 or 1, that is r, right? And then we take that rth index of the x. Now x is one of the entries of the lists, so we take rth index of that, and that gives us p. So this is basically randomly selecting one of the two, right? And we have now p. Now we concatenate that p and send it through Alice, and we get a ciphertext c, and then we concatenate that ciphertext c with k, send it through Bob, we get pb, and then we concatenate all of the three, p0, p1, and c, and we detach it from the graph and send it through Eve, and we get r of Eve, meaning that it's estimation of what the output should be. Now, Eve's adversarial loss is measured by the criteria. The criteria in this case means the loss function. The loss function measures how different it is from the actual value. Now this actual value is just a tensor of uh, if if the if r is 0, then this tensor will be 1 0. If r is 1, this will be 0 1. So basically we're measuring Eve's output with relation to these two types of tensors. So yeah, Eve's adversarial loss is measured this way. Then Bob's decryption loss is measured this way. That we have how different Bob is from P, how different PB is from P. Again, the same thing. And instead of having just the Eve's adversarial loss in negative, we have 1 minus Eve's loss squared. This is something that's suggested by the paper, and it tends to work well, so you've used it. And again, now we set the backpropagation steps, optimizer step, again backpropagation, optimizer step. These three lines, they prevent exploding gradients by clipping the gradients at a certain value. Um, yeah, and this in this loop we measure how much Bob is wrong about the plain text, basically measuring Bob's accuracy, and append all of these to the lists respectively. G.
Ali Samar,
G.
you are listening to me?
Yes.
Explaining the code is not the best way. The present means way of presenting the things.
Yeah.
It is better that you make a flow chart of these codes.
Yeah, I think that.
And there you can important instruction you can write within the in the flow chart also. Because you are my student, I'm listening very patiently, and I'm having certain interest also in these topics. That's why. But examiner may not give you such a long time.
Right, so right.
And
That's why I had this sort of structure so that we can see.
left, many friends left. So
Yeah,
just
sure.
to make it more, it is responsibility of the means person who is presenter that make their presentation interesting.
Sure.
So इसको जरा flow chart से, because you are having a command on the Python programming and the subject whatever you are implementing. So wherever if examiner asks the question, you can show anything,
Sure.
whatever you wish, which can defend whatever you want to defend. So it is better that you, because you see your input, your back propagation, then your distance measurement, then means forward. All these you can show through a network, also through a flow chart also.
Yes.
This training process.
Sure.
And,
I'll do
and
that.
then
Yeah.
plotted result, how your error is loss function is decreasing and converging, that you can show.
All right. All right. So yeah, again we have the same types of graphs. We have the adversary. Without the adversary, you can see that the networks, they try to learn, and they do indeed converge. And then with the adversary, this is the better result that we got. This is the main result that we want to show. That by introducing the adversary, you can see that the rate of loss decrease has decreased quite a bit. Now the loss doesn't go down as quickly as it was. So this means that the adversary is having an effect on the two networks, and we of course have to do further experimentation with these to get a very accurate result. But this is some of the good results that we had. So yeah, so the results again, the rate of loss decrease is reduced, stronger encryption is learned. And if there are any questions anyone wants to ask right now, they can. I'll be happy to take them.
My question is that when you are checking the accuracy with the unforeseen data,
Yes.
like means I'm talking about the validation testing kind of thing,
Yes.
then what is the performance of your network?
Yes, the performance of the network with unseen data is. I'll have to.
Similar.
It's not similar, of course, it's reduced, but it does give us a decreasing gradient. It does give us a decreasing loss. And although the loss is not it's not perfectly going down, but it does tend to reduce.
Once you are satisfied with the training of your network,
Yes.
Means both the networks are trained properly,
Yes.
and it is stopped, stalled,
Yes.
then you are using another set of bits, you are encrypting it,
Yes.
you are getting a ciphertext, then you are giving this to the both the networks, your ad- adversary as well as the desired network, and then what is the performance, that what you are supposed to show.
Yes. So
O-
see, this
Only
graph is showing the training
because
performance,
what
but
data you are using, it is same as that of your training data.
yeah.
So other than training that
Yeah.
only then you can say it is a.
Of course, of course. When I do the final thing, I will include all the things. The thing is that we didn't have a satisfactory, I didn't have a satisfactory loss with that to show. So that's why I showed the training loss decreasing. Anyway, so that is one thing.
Someone you are having good knowledge of whatever you are doing. I
Hmm.
appreciate it, but one thing I'm finding that you are not able to do,
Hmm.
that you are not able motivate, and you are not able to educate your group partners also,
Oh,
because group activity, I
yes,
told
sir.
you in the first also.
Yes, so the thing
And
was that
in
the thing was
go
that
into the field,
they were actually
uh,
helping me with the research and all, but the two of them,
see that
couldn't.
everybody have same level of knowledge. Obviously, those who are giving more time, more efforts, obviously they will have more knowledge, and it will be reflected in the presentation.
Yes,
But you have to carry along all your, because this is a group activity. That's
yes,
why I'm saying.
yes, yes.
Okay. So finally, in final presentation, if you will blank all your partners,
Yeah,
then they will get time in final presentation also. They
yes,
won't be able to do anything. Anyway, it's not like that. If you'll train them, if you'll take them along, then your marks will be less. You will always have more marks.
yes, sir.
है ना? So that is, and in future also, when you will go in the field, you have to work along with the people in group. Nowadays, it is very means obvious thing. So that is also a kind of training.
Sure,
Okay.
sure, sure. I'll include
Okay.
them more. So just the conclusion, and we'll look at the synchronization between Alice's Bob is achieved. The bit error we have to improve on. I'm just quickly finishing this off now, and the experimentation that has to be done further is that we will try to use text embeddings and autoencoders, and we will try to improve the loss reducing. The improvements are these, that we need a better encryption model, because when we talk to our guide also, he has looked at this and suggested that yes, this is working well enough, but we need to find a better version of this so that we have some of our own work as well. Now, yeah, so these are three of the things, and that I hope to improve on, and some of the references that I've been using. And that's about it from my side. Thank you for listening patiently for so long.
Okay. Thank you.